Okay, so this is an image of the sun in extreme ultraviolet. It's a spectral line that is roughly showing you plasma at 1,000,000 degrees Kelvin. So it's pretty hot. And this is in the corona, the outer part of the sun, which is outside of the visible surface. And what we see as the visible surface as we're looking is about 5,000 degrees. But then the sun heats up for a whole nother talk's worth of reasons as you go out from the sun for a while. And eventually, as you go towards Earth, it cools down again. But the plasma right near outside the sun, the corona, is roughly 1,000,000, 2,000,000 degrees on average. So the main point here is that the entire solar system is always bathed in what's coming out from the sun. It's bathed in the magnetic field. Our magnetic field is basically very much like the Earth's magnetosphere. It shields our entire solar system and beyond from interstellar space. And so we have kind of an encapsulated heliosphere, and then within that, the planets that have magnetic fields have their own magnetospheres and so on. And that helps shield us from some cosmic rays, although not all of them. So basically the key, and I'll show in a minute what I'm talking about, to understanding space weather is to understand the interaction between magnetic fields and plasma. Plasma meaning ionized gases, for anybody who may not know that. And so if we understand what's going on with the magnetic field, which we don't entirely, and if we understand exactly how the processes, the physical processes in the plasma and interact with the magnetic field itself, then presumably we could understand everything about space weather. But we don't. So all the features that we're seeing here, now that I've lost the...
Oh, run by the projector.
Okay. So all the features that we're seeing here are basically governed by the magnetic fields. Up here at the solar poles, it looks kind of blank compared with the rest of the sun. And what that is telling you is that the field there is open, meaning it extends out into the heliosphere and doesn't close back down. Well, ultimately it closes back down there, but for all intents and purposes, these field lines are open. And that means that particles and mass and so on can stream readily from the sun air. In that region, that's where the fast solar wind comes from. These regions here, now this is showing near maximum, near solar maximum, a time of great activity, and there are these activity bands where sunspots have emerged, and you can see that they're really pretty confined to certain mid-latitudes. And these active regions are places where the magnetic field is very strong, and that's where the magnetic field also can get very tangled up and give you eruptions. In particular, these long linear type features, they're dark in this image because they're actually cooler. There's cooler mass there, so it's absorbing. Those regions are where the field is most strongly built up and tangled, and that's where most of the strong eruptions come from.
Is that a sped up video or the solar?
Yeah, it's not in real time, but the solar rotation rate is about 27 days. So we have one side of the disk will be facing us for 2 weeks roughly, and so all the activity that's heading out towards Earth, more or less, will come from the side that's facing us. So this is showing about 4 or 5 years, maybe about 4 years of the solar magnetic field that's been modeled through an assumption that the field doesn't have any forces in it. It's kind of the simplest possible, most relaxed magnetic field. Now, that's really true for most of this, but when you get down to these really complicated regions where the sunspots are popping up and where this tangled magnetic field is popping up, then that's really not a good assumption. But it's showing you how complicated the sun can be and what types of regions you have. So here, where you see the field lines go from one place on the sun to another place on the sun, those are what we call closed magnetic fields. And these are, as I was saying before, in the poles, you have what we call open magnetic field where particles and mass can stream out. So the interesting thing here is that you're going from solar minimum early on when there was really nothing showing on the sun, to more and more of these active regions containing sunspots showing up at later times, and complicating the magnetic field immensely and giving you opportunities, lots of opportunities for eruptions to occur. So one thing I wanted to stress actually is that the so-called quiet sun, when it's not erupting, when there's a kind of featureless in there, that still, it gives us space weather. And in particular, one thing it does is create the ionosphere. The ionizing radiation from the sun is why we have, why our atmosphere isn't all neutral, and it's why we have ionosphere in the first place. So solar wind and the quiet sun itself also have effects on space weather. And in particular, this was supposed to be okay. So everybody's heard of the solar cycle. You know, we have this 11-year or 22-year, depending upon whether you want the sun to just reverse once or go back to its original magnetic field orientation. But the solar cycle here is illustrated just 11 years of it, as seen in the extreme ultraviolet again. This is looking at 100,000 degree plasma. No, actually, sorry, this is looking at again, the corona in hot plasma. And here it starts at kind of a very low minimum where you can see that there's nothing on the sun. And gradually you get, over the next several years, you get more and more of these active regions coming up. And the reason I'm showing you this is to show you the connection between this type of solar variability, just the rise and fall in the amount of magnetic activity on the sun, and some of the features of the ionosphere. This is showing just simply the total electron content. When it's more ionized, you have more electrons. When it's less ionized, you have fewer electrons, basically. So, and this is showing you that this is a radio indicator. This is showing you the frequency, the cutoff frequency. Above which or below which?
Anything higher than that will penetrate through the ionosphere.
Right, anything higher than that. So, this is around 10 megahertz or thereabouts on average. So one of the interesting things is that this past minimum was a really low minimum, and our maximum was kind of a really weak maximum. And the last few have been kind of heading downwards. So one thing we're wondering, and a lot of people are wondering, is are we headed toward a really, really low period of solar activity? We don't know yet. The models are not good enough, and the theory is not good enough. But it's definitely a question. Okay, so let me move on to solar eruptions. This is showing you, again, one of these EUV images of the rotating sun over quite a long period of time. I think it's about several days, because it's not this is not quite giving you a full passage. And this is showing you out of, let's say, 2 solar radii on out to about 6, what a white light coronagraph sees in the plane of the sky. And you can see 2 things here. One is kind of the steady blobby stuff, sort of diffuse blobby stuff. This is basically the chunky solar wind. And blobs were actually the official term for the stuff coming out of the little things that you see in here. And people can track that, and they can use that to track the solar wind speed. But these big things are the solar eruptions. And those are tied in with activity on the surface, and you can sort of see it, although it's not very spectacular compared with what you're seeing in the coronagraph. You see the flare down here on the surface, and you see the coronal mass ejection. This is showing you density, basically, in that type of image, but it's accompanied by a magnetic field, strong magnetic field coming out with it. And these are the most energetic explosions in our whole solar system. So we already talked about this because I had a good question. This is the time scales involved with space weather. 8 minutes for the radiation, that flare radiation that you're seeing getting to the Earth. The particles reach the Earth in, at very least like 15, 20 minutes, maybe an hour or maybe a little longer, but they can get here a lot faster because they're semi-relativistic. And then finally, the CME itself gets to Earth in 1 to 3 days. So just to show you what some of the flares look like. Oops, sorry. Yeah, this should be starting it. So this is the so-called Halloween flares in 2013, which were really large. And this region, you can see this region light up. This is 10 million degree plasma. And this is even not the hottest plasma that you get. You can get up to 100 million degrees. At that point, it's really not thermal, you know, it's probably non-thermal plasma, but this is basically the hottest regions in which these flares occur. And this type of radiation, of course, penetrates much deeper into the Earth's atmosphere than does the 1 million degree plasma that I was showing, or sorry, 1 million degree radiation that I was showing before. So another thing that happens in addition to that radiation that you get are the CMEs causing great big particle storms, as I said before. Let me see if I can stop this thing.
Is that the detector getting overloaded essentially?
Yeah, what this is showing you is, okay, yeah. So this is the CME coming out. It's kind of what they call a halo CME. It was from an event that was on the disk. So you're kind of, since this is just showing you the plane of the sky, it's coming at you in all different directions, and it's actually harder to detect these things coming straight at us than it is to see these things going off to the side, which is a reason why we'd like to have coronagraphs all around the sun. But you're already starting to see this snow around there, and what that is the particles, the first particles hitting the detector. And this detector is out at Earth orbit, so basically these are the first particles get there, and then you can see it get worse with time, because then the slower particles get to it later. So why does this happen? So very simply put, and I can answer questions later because I don't want to take too much time on this, there's a process called magnetic reconnection. Anytime you have field lines that are oppositely directed, like in this very simple image here, movie here, they can, if they get close enough to one another, they can kind of diffuse together, and you change the connections. You change basically the foot points of those field lines. You can get closed field lines interacting with other closed field lines, or open with closed, etc. And this can happen in a number of places. It happens down in those tangled regions on the sun that give you the flares and the eruptions together, but it can also happen at when these CMEs, which have their own magnetic field, CMEs are coronal mass ejections, sorry. When they come to the Earth and they approach the magnetic field of the Earth, if they're oriented correctly, or incorrectly, whatever, they can reconnect, and then that allows a lot more particles and mass to get in. And changes the activity. In the Earth's magnetotail, the back end of our magnetosphere, where field lines again can get drawn out and come close together, you can also get reconnection there as a result of these geomagnetic storms of the CMEs hitting the Earth, hitting the magnetosphere, and those things then reconnect and bring particles and mass, etc. in. And another thing that the reconnection does for you is it converts magnetic energy. You have magnetic energy coming with these things. It liberates that magnetic energy into the form of kinetic energy. You get flows coming out of it, and you also get particle acceleration. And ultimately, you get thermal plasma. It heats up the plasma with it. So you get all sorts of signatures. That's why you get the bright flare, for example. So this is just showing a model that illustrates what happens with the reconnection. There's reconnection going on between sort of the green field lines and the red field lines here, and then there's also reconnection happening back here. So the reconnection happening back here where my cursor is what gives you the flare, but it also essentially untethers what becomes the coronal mass ejection. And you can also, excuse me?
Cuts its roots in a sense.
Yeah, in a sense, that's exactly it. So you kind of need both. You need something that gets rid of the field above it that's in the way, and you also need to liberate it from below. The other thing I wanted to point out in this is a model that was done by one of our postdocs. This is the shock that was driven ahead of the coronal mass ejection, and that's where the protons and things are accelerated.
The last sentence was too.
I'm sorry, that's where the protons and the solar energetic particles were accelerated at those shocks. I thought you'd be interested in seeing what the sun puts out in the radio. So this is a radio spectrogram from Caldera from 2006, just I found on the net. This is, there's a whole bunch of solar philately, if you want to call it, solar stamp collecting. Type 2, this is called a type 2 burst. And what it is radiation associated with that coronal mass ejection shock that's headed out towards the Earth. And what's interesting about it is that you can get the speed from the slope of the change in slope, and you can also get an idea of the density because the emission is related to the density in the location where the emission's coming from. And there's other types of emissions too. It's possible, since I don't know this event in particular, but these sort of vertical activity here could be coming from electron beams. And they also are created by the flares, and mostly by flares or by jets on the sun. They have type 1s, all the way up to 5. So finally, once you start out, you know that there's a CME, how can we predict what's going on with it? This is a simulation done by people at the CCMC, the Community Coordinated Modeling Center at Goddard, in my lab. And what they do is they use this three-dimensional model to insert a coronal mass ejection at 20 times the solar radius. So they don't start at the sun for various reasons, but they do start further out once they know where it's coming from and kind of what the size of the region is to start with. On this plot, you see the Earth is this yellow thing here. The various, that's stereo A. Okay, so there's a coronagraph and other things out there. There's some planets on here. I think that's Mars over there. And the coronal mass ejection is that big arc-shaped blob that's coming out. This one obviously was headed right toward the Earth. And they can make an estimate of when they expect this to get to Earth from this view. This is looking down on the ecliptic plane. This is looking kind of from the side. This is as if you were at Earth with this sort of panorama view going by you. So finally, I just wanted to give you some links if you wanted to look at where, places where you can predict or just see what the sun is doing or what the Earth's magnetosphere, et cetera, are doing at any given time. There's a really great website from Tamitha. Do you know Tamitha? Yes, oh, thank you. Okay, so you guys already know her. I met Tamitha, I think, before her last name changed. It was Mulligan, I think, before. Anyway, so she puts out not only predictions, but she also has really nice explanations of what's going on. NOAA runs the Space Weather Prediction Center, and they're the official provider of operational space weather forecasts for the government for the Sun-Earth line. But outside the Sun-Earth line, in other words, for spacecraft, NASA's robotic missions, anywhere else in the heliosphere, we do the predictions. And so the Community Coordinated Modeling Center, which I just mentioned, they do a whole bunch of things, including doing these forecasts for the NASA missions. And they also have some really nice stuff on their website. This ISWA application is a web page that you can use to look at all sorts of different data streams and modeling, as well as actual data coming from various satellites all over, and as well as ground-based data. So let me turn over to Doug.
Well, before you do,
Yeah.
when is your laboratory going to reclose all the breakers so that we can get some decent radio propagation?
What?
In other words, when is your lab going to set the sunspots loose so we can offer it?
Yeah, we wish. You know, it's really boring when we don't have any activity, and it's harder to convince Congress that we need funding. So, you know, I'd be very afraid when there's a lot of solar storms, but if there's not a lot of solar storms, they're not so excited. Okay.
Let's ask questions as we go, because there's a lot of material here, and unlike the sun, where there's one sun, we have only one Earth also, but there's a lot of different pieces, and they're all a little different. So the basic idea is space weather, as Judy said, occurs throughout the heliosphere, but mostly, we're not on Mars or in a robotic spacecraft out there, we mostly care what happens at Earth. So Earth is where I think of the home of space weather. And so this is what Judy had mentioned. This is the Earth's magnetic field on the right. It's a little hard to see with the light. And the thing that's coming from the left is this coronal mass ejection that's bringing extra mass, extra momentum, and extra energy towards the Earth. There's a couple of features that happen. This magnetic reconnection, normally what happens is, the reason magnetic reconnection is so exciting is normally the plasma on one magnetic field line and plasma on another magnetic field do not mix. If you have cold plasma here and hot plasma here, they can sit right next to each other, they don't touch each other. And also, they tend to kind of move around each other, they don't tend to coexist in the same space. When you get magnetic reconnection, you can have those two groups diffusing together, repartnering with different flux tubes. You can mix those two plasma populations. You can also get the phenomena that Judy mentioned, which is you convert that magnetic energy into kinetic energy. In addition, you can extract the kinetic energy of the solar wind, which is 400 kilometers per second or 2,000 kilometers per second in a strong CME, streamed by the Earth. You can convert that and basically using a dynamo, magnetohydrodynamic dynamo, that extracts that energy and drives currents through the ionosphere, which is sort of your resistive load, and that heats the atmosphere and a lot of things like that. So the whole magnetosphere is kind of a dynamo-powered system that is run by the solar wind. So I'll just play this again. You can see on the front, the magnetic field in the solar wind is not shown, but you can see that magnetic field on snapping, reconnecting with solar wind magnetic field, and then flying back into the magnetic tail. The other piece that happens is then you get a second reconnection event. As Judy mentioned, the magnetic tail, which is sort of a windsock streamed behind the Earth, that has magnetic fields which are oppositely directed. And if they get compressed or squeezed together, they tend to reconnect. And what you get is this rubber band snapping, this release of tension, that tends to take that stored magnetic energy, which is trying to squeeze it together, and releases that and sends energy back towards the Earth. And so this is what's known as a magnetic substorm. These are associated with auroral displays at high latitudes. They're associated, you see the aurora there indicated. They're associated with local radio propagation issues, mostly high latitude issues. A lot of features we'll talk about here are high latitude because that's just like on the sun. As Judy said, when you have the open magnetic field, plasma can free stream along that magnetic field line. On closed magnetic field, it's more of a bottle, like we were talking about the radiation belts earlier. That's a region where it's kind of stably trapped and it can't really interchange from one to another unless you have magnetic reconnection happening. But on those open field lines, energy can come in and it can go out. Plasma can come in and can go out. So high latitude regions, sort of above, Montreal, typically, in our side of the hemisphere, that's where you start to get these open magnetic fields, a little further north even. And that's where you get the auroral activity, that's where you get a lot of these other phenomena. But that doesn't mean we don't have space weather here, we just have different times. So just to show you a more, that was sort of an artist's conception. This is an MHD model, very similar to the one that Judy showed of the sun. And this is the Earth's magnetic field, kind of nicely shown as being buffeted by this dynamic solar wind, which is constantly changing. It's constantly changing velocity, intensity, temperature, magnetic field strength and direction. And what happens in that direction, it's flipping around all the time. It depends on what part of the kind of current sheet we're in. The magnetic field can be pointing this way or that way, and it can be pointing up or down. And as Judy mentioned, it's sort of a key that unlocks that process when the magnetic field points down or southward in the solar wind. That's opposite the Earth's field at the subsolar point, which is pointing northward, and that's the time we get lots of reconnection. When the solar wind flips around to be northward, we don't get a lot of interaction. It's basically not a very efficient generator, and all that energy is just kind of deflected around the Earth and streams off into the tail. So this is sort of a nice movie that shows some of those features. And you can get a sense for, again, it's sped up, but you can get a sense for how dynamic this region is. These magnetic field lines are not this kind of static picture of the magnetic field. Close in and near the equator, the magnetic field is very stable and strong. But as soon as you get outside of geosynchronous orbit or near geosynchronous orbit, the magnetic field is dramatically affected by the solar wind. And all these tugging and twisting and compressing, this is a case where the density is heated up. You get a shock that's much more intense in the front end. You think of it as like a rock in a stream, and this supersonic flow is just either being diverted around the magnetic field of the Earth or kind of interchanging energy and momentum.
So, like geospatial satellites are out there, when you do that, on that picture, where would they be? Are they?
They're about where the magnetic field line closes, goes from being closed to open. So if I had a, so more or less, and that boundary moves back and forth. It's actually a really interesting region. They're about here, about 6.5 Earth radius away from the sun. So sometimes that's in a stable, steady region where it's completely closed and not too distorted. But it's also a region where you can strongly distort the magnetic field. You can get strong currents, radiation belt enhancements, and so on. It's typically at the tail end of the radiation belt, at the outside edge, but sometimes we can get enhancements of the radiation belt that's too fast. What happens to all that energy? So when you see all this flailing and buffeting around, some of it gets discarded down the tail when you get this reconnection event and the magnetic field snaps like a rubber band. Part of it goes towards the Earth and sends energy into the atmosphere. Part of it just streams out as a blob of plasma, kind of like the blobs that Judy showed, or analogous to them, where they're just being shot off into space. So some of the energy gets lost that way. A lot of the energy gets turned into the form of energized electrons and ions, sort of semi-stably trapped around the Earth. As the ring current is a phenomenon that exists there where you have 100 kilovolts oxygen and hydrogen ions. You have electrons about the same similar energy. The radiation belts are another factor of 10 higher, sort of million electron volt electrons. Those are the ones that can damage satellite electronics, for example. And so those are areas that kind of at least temporarily store a lot of the energy. The radiation belts can store energy for many years, but they don't store a lot of the energy. There's a lot of, each particle is very energetic, but there aren't that many of them. Where you get a lot of energy dumped in is in the atmosphere. And that comes in two forms. You basically get heating of the atmosphere, three forms. Heating of the atmosphere, ionization of the atmosphere to form your favorite thing, the ionosphere. And the third thing is sort of energy and momentum transfer where you can sort of stir up the atmosphere and make some basically wind at those high altitudes. And the winds can drive currents, which then do things like induce the telegraph operator fires that we heard about earlier. This is a picture of a couple different paths by which energy is deposited in the upper atmosphere. We're talking about the region sort of from 25 miles on up to 300 miles, so bracketing the space station, and sort of starting just above where high altitude stratospheric balloons are launched. And so that region is described usually in terms of the temperature profile. We start at, room temperature, approximately the troposphere, up to 10 kilometers. We go to the stratosphere, which the temperature is more or less the same, but it's a little bit kinking up. And then the mesosphere is where the temperature has maximized and goes down to the coldest place on Earth, which is the mesopause, this region where the end of the mesosphere is. That place can be 150 Kelvin, or approximately half the temperature here. And it's extremely cold. You get things like noctilucent clouds forming there, if you've ever seen those. High altitude, night shining clouds that you see right at sunset, because this part is in darkness, but those clouds are still in the sunlight at 80 kilometers altitude. Anyway, so that's the atmosphere, and above the mesosphere is the thermosphere, so named because the temperature shoots up. It goes from 150 C, the mesopause, to 150 Kelvin, to 1,000 Kelvin or more. And it's essentially a flat temperature profile at some point due to the various phenomena. The density, which is also something we all care about, starts out at our 1 atmosphere here, and it falls off exponentially, essentially, up here. And so there's still atmosphere here. When you're at 400 kilometers about here, the space station is orbiting, but it will come down if you don't do it. It's like Skylab, if you remember Skylab. If the density of the atmosphere becomes higher than we expect, and we don't reboost it, in time it will deorbit. And that deorbiting time can be months to years, depending on what part of the solar cycle you're in and how much energy is inflating that atmosphere. So that's sort of the region we're talking about. I mostly focus on the thermosphere and ionosphere, but I have people in my group that do the mesosphere as well. The ionosphere coexists with this region, and it's the ionized portion of this neutral gas. So the neutral gas is relatively in our world, very dense, and the ionized fraction might be 1 part in 10,000 at the low altitudes. And then as you go higher and higher, the ionization becomes more and more a fraction of the total gas, until at the top of this region, it's all ionized. So in the sun is so hot, it has also a region where you transition from neutral gas to ionized gas, but that happens in a different altitude region. But for the same idea, you have sort of a temperature change and ionization sources that can tend to drive that ionized plasma. So it's kind of an interesting region because you have both ion gases and neutral gases, and they behave differently. The ionized gas is much more the plasma that Judy had mentioned. It's driven by electric and magnetic fields. It has to be basically confined by a magnetic field, and if an electric field is pushing, it tends to move perpendicular to the electric and magnetic fields. So you might be up there, and you might feel a wind kind of whipping around. It changes the ion field wind changes very rapidly on time scales of minutes, and it whips around, and it's very hot gas usually, and it's blowing in a certain direction. And if you happen to be up there and not asphyxiating to death, you would notice a very strange phenomenon. You'd have two winds blowing on you at the same time. One would be this ion wind, whipping around very fast. The other one's this very slow neutral wind, just like we have here. We don't call it a neutral wind on the ground because it's just a wind. But there we have to make that distinction because of these two gases. We call it a neutral wind. And that neutral wind can take energy and momentum across the magnetic field. So the ions have to stay kind of locked into their magnetic field region. The neutral wind takes energy, say, from high latitude region where it's dumped in, to lower latitude regions like where we live. So the neutral winds are very important and have not really been fully understood. But essentially you get the same kind of temperature, same kind of weather we have here, you get there. You get high pressure zones, low pressure zones, strong winds, slow winds, all that sort of thing. The only other piece that happens that's very interesting is if you go anywhere on the Earth or even up to Mount Everest, essentially the composition of the atmosphere is the same. If you were to measure how much oxygen there is, how much nitrogen, how much argon as a percentage, you get the same answer. The density changes, but it's very well mixed. At these altitudes, there's not enough collisions to mix the gas, and so the different heavier species tend to stay down low and sort of separated. And as you go higher and higher, you get the lighter species. So nitric oxide and CO2 and these sort of things, like O2, are down low at 100 kilometers, 120 kilometers, 200 kilometers. And as you go up, it changes to atomic oxygen and then hydrogen as you go up higher. So there's kind of different phenomena up there, but it's an interesting spot.
Where's the ozone layer?
That's in the stratosphere, and
That's
so
way below here.
some space weather actually has to do with the stratosphere. We'll talk about that at the end. But I just wanted to talk about the pathways for this energy deposition. The first one is the extreme ultraviolet and X-rays that Judy had mentioned. So this is wavelength. This is the really short wave, high energy stuff. Visible light starts about here. And this is how low in altitude that radiation penetrates. So visible light penetrates to the ground. Thank goodness. I guess we're evolved to see that because that's what it is. But if you go to shorter wavelengths, higher energies, the atmosphere stops it. If we didn't have an atmosphere, we'd all have a terrible case of sunburn. And this energy that's soaked up by our thermosphere will be soaked up by our skin. And so it's good that it happens. But what it does is, that's the reason the thermosphere is so hot, essentially, is you're really depositing a lot of energy at those high altitudes by direct absorption of solar ultraviolet. That solar ultraviolet is the main driver of the atmosphere, upper atmosphere. The thing about it is, except for solar flares, it varies only slowly. You know, as you can imagine, as Judy was pointing out, these active regions maybe are brighter in the ultraviolet. And what you see on the Earth is kind of the integration over the entire disk. If you have a little bright spot here and bright spot here, and it's cool here, you just get to add it all together, and the average is what you see. So, but as those bright spots rotate around, the Earth is going to see a slow modulation in the ultraviolet, but it's not going to be super rapid. And then on solar cycle scales, we get a big modulation in the ultraviolet. So for the most part, it's the most important piece, but it mostly happens in summer, so it doesn't happen in winter at the polar caps where there's no light at all, and it doesn't vary super quickly except for during solar flares. So we need to understand that and understand what it does, but it's not our day-to-day space weather driver, except for the flares. What does vary rapidly are this is that solar EUV radiation that's absorbed here. The magnetosphere, this magnetic field that I mentioned, that has these energization events that shoot electrons essentially into our upper atmosphere and drive electric currents in our atmosphere. That's highly spatially variable and also highly temporally variable. It can change on time scales of minutes, and you can have structures as small as 100 meters wide, ranging to thousands of kilometers wide. So this is primarily high latitude, and so the main area, this comes in mostly low and mid latitude, this comes in high latitude, and then we have to, somewhere between, sort of a balance where the different phenomena compete. There's yet a third piece, which I'm not going to talk about today, but it's actually recently becoming important and interesting, which is terrestrial weather that we live with here does, of course, propagate up, and different effects of that can propagate up and also modify this region. And during solar minimum periods, when the sun is quiet, the magnetosphere is quiet, this can be the dominant thing that drives our phenomenon. And the problem with that is we don't understand it. And you'll be looking at, say, a TEC map to try to predict your propagation of your radio waves. And nothing will be happening in the sun, nothing will be happening in the ionosphere currents, and all of a sudden, from one day to the next, the TEC will go crazy. And what we think that is due to is some kind of neutral atmospheric motions that are generated down low, and they slosh back and forth. The atmosphere is kind of sloshing back and forth, and if it hits a certain phase, you can couple into that ionosphere and change the ionospheric density. That's something that's currently being studied by the ICON gold missions. Gold has been up for about a year, and ICON has just launched. So that's where the energy deposition happens, and this is that atmospheric weather that I mentioned. This is again looking down at the North Pole. This is the quiet time kind of behavior. The ion wind that I mentioned, the neutral wind that I mentioned, the temperature of the gas, and the density of the gas. And this is what happens when you have a geomagnetic storm. You can see, you can't really see what's going on, but there's a lot more stirring up of this. Kind of think of it as dragging a spoon through your soup, and you get these convection cells, these double convection cells that appear because the plasma is being dragged around and it has to return flow. The neutrals actually get dragged around by the ions. The ions basically run into the neutrals and start to slowly modify the neutral wind pattern, and you get a bigger wind there. You also get much hotter gas during a storm and higher density, and this is going to factor in when we talk about orbital drag and sort of space weather impacts. But when we talk about electric currents flowing overhead in the ionosphere, that's due essentially to this ion motion relative to the neutrals. And as that ion motion changes different conductivities, the electrons and ions diverge, and you can have a net current. They're not, the whole plasma is not moving together as a unit, and that's what drives your overhead currents, which can be the ground-induced currents. So this is just the kind of picture like you might be used to from either if you're looking at Ionosphere data to kind of check out this maximum usable frequency. This is that plot essentially Judy mentioned. This FOF2, which is the frequency of the F2 peak. This is the maximum usable frequency here at a particular day and time. I'm not even sure what station this is from. These have been operating since the discovery, essentially, of the ionosphere back in the 20s or whatever year that was. And they basically scan in frequency from 100 kilohertz to maybe 13 or 15 megahertz, and they just range gate what's happening. So it's like a speed gun on a police car. Basically, range gate. How long does it take for that signal to reflect back down to the ground? And they convert that to a altitude profile of the density. And so that's something that you can do. What you also see from that is you see the variation, daily variation, or solar cycle variation of that maximum usable frequency, of the altitude profile, which controls your index of refraction and your propagation path. You also get turbulence, and some times when this very smooth profile gets highly distorted, and you get, I'll talk about that later, you get these highly distorted curves which lead to radio frequency interference and scintillation. So this was sort of the picture from one location, just looking straight up and making a local measurement. This is more of a continental US view. This is the same thing that Judy plotted before, which is the total electron content. And this is typically gotten by GPS receivers on the ground, looking at the GPS receivers in space. There are two frequencies in the gigahertz range. And by looking at these, they're slightly different. By looking at the relative phase shift between those two, you can tell how many electrons there are between you and the GPS receiver. And most of those will be below 500 kilometers. So they kind of convert that into a two-dimensional map, and you can kind of see these waves. This is during, I guess, after the Halloween. There was another storm in late October, Halloween of 2003. And you can see these waves of higher electron density kind of sweeping across. There's a really big one that comes later. The thing about that is this electron content, changes the refractive index of your radio wave. So all of a sudden, you thought you had a nice smooth ionosphere to propagate your rays or bounce off of them. And now you've got local patches that are very intense. So that can really modify your abilities. So we talked about, that was welcome to geospace. Now we're going to talk about what are the typical effects. Space weather, we talked about radiation impacts to satellites, astronauts, and airplanes. This power grid damage that we talked about. Orbital drag, where it's not only increased but also variable, and it's hard to predict on these low Earth orbiting satellites. And then, of course, the one we all care about here, radio signal propagation for communication and navigation purposes. So these are the radiation belts we mentioned. Sort of this donut-shaped, we kind of made a cross-section, we cut out this section. But these are the torus kind of stably trapped particles, and the color indicates the flux, how many electrons there are. And you can see this is days counting up here. On an hourly basis, this whole thing is breathing in and out, it's changing. The colors are changing because the intensity of the trapped radiation is changing. We used to think this happened only in extremely slow timescales because originally, when the radiation belts were discovered, they were deduced to be from cosmic rays coming and hitting the atmosphere of the Earth and generating neutrons, which then decayed to form these radiation belts. So that's a very slow process. In fact, we now know there are many plasma wave processes and storm time processes that can make variations on this in the timescale of seconds. There was a famous event in March of 1991 where one of these shock waves that Judy mentioned came in from a CME and slammed into the magnetosphere, basically compressed this whole region. And it just so happened that that was perfectly timed and perfectly situated to drive a shockwave deep into this region, which usually doesn't happen. Usually this is kind of protected from no shockwave. When that shockwave came in, that electric field basically just rapidly accelerated electrons by orders of magnitude. And suddenly we had basically a new radiation belt that was formed in a period of seconds and lasted for years. So it's events like that that, of course, if you have a satellite in this region, this is higher than our low Earth orbit, but GPS lives in this region, geosynchronous satellites live in this region. You want to know ahead of time, if you can, what the environment is, or at least know what it is at any moment. Because what will happen is these electrons will either degrade the life of your satellite, or they will introduce spurious commands in your satellite, for example. Here, was there a question? Okay. This is a picture of the radiation dose. There's another thing we really care about that CCMC is doing some modeling on, and NOAA is doing some modeling on. This is just a picture of the radiation dose versus altitude relative to sea level. So in a 25,000 foot, you're already 10 times sea level. When you get to a high altitude plane, 40,000 feet, you're 30 or 40 times sea level. And if you're in one of these stratospheric balloons, which probably we're not going to be riding in, but we do send instruments there, it's 60 times sea level. And that's for a particular average time, which is maybe closer to solar minimum, I guess. Solar max. And then here's an example of how it changes with latitude. So again, these planes that are flying over the high latitude regions, already, even on a quiet day, they already get a factor of 2 or 3 radiation dose relative to a low latitude plane. But that route is shorter, quicker, more efficient, so you want to fly there. But you have to consider, maybe for the average person who maybe makes it 1 trip a year or whatever, you can deal with it. But the flight attendants, the pilots who are on those flights every day, they accumulate rapidly a very strong dose. And then if you get a solar event, you know, you can imagine it's going to get much higher. And so trying to understand those dose levels and trying to give us enough warning so that the FAA can say, well, hey guys, probably not a good idea to fly at high latitudes today because you're about to get a solar energetic particle. The ground-induced currents are the thing we talk about with the Carrington events. They're showing up as telegraph lines because we don't have telegraphs too much anymore. The main effect now is the power lines. And essentially the idea is you get these overhead ionosphere currents, which are essentially driven by this, the plasma starts moving, and because of the collisions with the neutral atmosphere, the ions go one direction, the electrons go another direction, and you get a net separation, and that drives a current over your head. And these currents can be quite intense. You can have many megaamps of current flowing in this current system. And they induce a current in the ground. If the ground happens to be particularly conductive, you get a very large current in the ground. And then if you have a long power line that's aligned along that, and it's in the wrong orientation, and it's very long, you can get a large potential developed across that, and that can blow out transformers, as happened in 1989. This is a famous story from Quebec. Various other operator errors and sort of loads in the system that caused it to be vulnerable. But essentially, there was this big storm in 1989, knocked out a major transformer and damaged other things that basically gave you a blackout here and major impact on the rest of the power grid, because there was a lot of sharing of this load. So this kind of thing, it's mostly a high latitude phenomena, but during extreme events it can happen just about anywhere. And it's exacerbated by ground conductivity changes, which are very highly variable throughout the world. One more piece that we looked at is orbital drag. And this is essentially that headwind that you get when you're at a satellite below about 600 kilometers. Above 600 kilometers, it's pretty meaningless. There's not much there. On the very long time scales, you would have to worry about it. But here, below about 600 kilometers, your satellite might last anywhere from 3 months to 3 years if you were at, say, 400 kilometers. And you'd like to know whether it was 3 months or 3 years. To do that, you've got to predict what the density you're going to fly through is, and the density varies with solar cycle. During solar minimum, you have a very low density, you can live a long time. Solar maximum, not so much. This is a picture that you've all seen of sort of the objects in orbit that are greater than 10 centimeters that JSPOC, formerly NORAD, is tracking. And they do that because they want to know if one of our rivals in the global world was going to destroy a satellite or put up a new thing here. They want to know, hey, there's a new satellite up there. We better know what it is and find out about it. So they track these other 10,000 or 100,000 events, and they like to know where they are at all times. The problem is, if you suddenly get a strong amount of energy dumped into the upper atmosphere, locally or globally, the density of the atmosphere changes, and you were predicting where these guys. You might measure them every few days with the radar, and then use a predictive model to figure out where they're going to be with an assumed drag force. If the drag force changes, and you don't get to remeasure them that often, you might be a few days before you can reestablish that, hey, yeah, that piece is the piece I was tracking last week. It just got a little drag, a little slowed down. So it's particularly bad because these regions of high density are not symmetric. So this is the day side of the Earth at high latitudes, the night side. If your satellite is orbiting this way, you see almost no change. If you happen to be orbiting this way, you see a factor of 6 higher density. So it's very spatially localized and also very, just very altitude dependent. A lot of things that we don't quite understand, so we're trying to make better measurements and models of that. This is sort of an idea of that satellite tracking problem. There's a famous plot from NORAD showing how many lost satellites they had. They usually had, at the time, I'm sure they do better now, they had sort of a low noise level of a couple hundred, things that every day they had to kind of check in and say, what's that thing? Oh yeah, that's the thing we tracked left. And they kind of lose, at the time, 100 or 200 at a time. When you get this big storm, then they've lost 1,500 for a day or two, and even for days after that, they're about double their previous loss rate. So that's just because they weren't able to accurately predict the orbits because they didn't know the drag. So what we're all here for is radio propagation, and I almost hesitate to show these slides because, again, you guys have been living this, and I'm relatively new. So, as you're all familiar, we use these in the megahertz bands and below. We can use the ionosphere to bounce waves, and we can also use it to kind of have long ray paths that are refracted through the ionosphere. We have sort of a typical case, multi-hop case with skip, and then there's other phenomena like blackouts, where you get one of these flares or shock waves that really changes dramatically the ionization in the atmosphere, and you basically have no potential region to propagate through for hours or a day, maybe even a day at a time. And so those are important if you're using HF radio to communicate. And if you're using some other system, maybe over-the-horizon radar works in a similar band. If you want to know when is that going to be operational, you'd like to know particularly this is happening.
Otherwise lovingly known as the Russian woodpecker.
Yeah. So here's a nice. I got this from there's a famous guy on the. He gave a nice sort of multi-page presentation. I don't know his name on here, but he gave a very nice sort of brochure on ionospheric effects of the space weather, and he compiled this list of this thing we call the K index, which I think is a Richter scale for the intensity of the storm that's produced from the space weather, and how that affects HF noise, aurora, and then here's some flares in a similar scheme, which is classified by the solar physicists. They kind of have a weaker flares at A, super intense flares at X, and again, kind of logarithmic scale. And they can deduce what you're likely to see in terms of blackout or absorption, and then sort of thing. So this is a nice figure, and what I want to show you is something that we might have come across in Judy's slides. This K index is sort of this Richter scale. 0 is ultra quiet, 9 is extreme storm. Carrington event was probably 9++. I'm not sure we would have that on the scale here. And then this is day by day for 4.5 rotation cycles of the sun, what the K index looks like on the Earth. And what you'll notice is it's kind of quiet, then it'll hump up, and then it'll come down. And this is for this month, so I think this is today, or last couple weeks ago. And then it'll go quiet, it'll hump up again, and humps up in almost the exact same place. And that's not an accident. That's a result of these active regions of the sun. Some of them come and go, but a lot of them are stable for many, many months, and they might evolve or change, but they come around every 27 days. And when you see them, that's a region where you're getting intense activity. So that's not an accident. This is a very useful thing if you want to predict, again, even just this 0th order thing, what am I going to see tomorrow? First place I would go is this plot, just to see what we looked like last month. Of course, there's much more sophisticated modeling, as Judy mentioned. But this is a very handy one, which is pretty easy to understand. Simulation is maybe my last major topic before I get a couple of advertisements. Simulation, is maybe you're familiar with, is the interference you get that takes your signal to noise and dramatically reduces it. Basically, you have a radio wave propagating through the ionosphere or refracting through the ionosphere, and what normally was a smooth system where you don't have this destructive interference, you now have a ripples or structure in the ionosphere, which basically means this part of the wave gets refracted differently, and this part gets refracted, and they have different phases when they come back into place, and they interfere. And so you get that for GPS signals, for communication signals, and simulations are one of the major things we want to learn how to predict. Why do simulations happen? There are different things that can structure the atmosphere. I showed you before that GPS total electron content, where there's waves of density coming through. But also you get these smaller scale features, which are called spread F. And this is a term that dates back to probably the 20s or 30s when they first discovered it. those ionosondes they were using to measure that maximum usable frequency and the altitude profile, they would see an F region, which was nice and thin, a nice trace. Occasionally, they would see it widen, so it spreads. And the reason it spreads is because you get this turbulence, and you're measuring for one moment, and the F region is here, and another region is here, and it kind of moves around a lot, you get a lot of interference. And this is what it looks like if you have a fancy radar that's operating at UHF frequencies. You can also image it, sort of. As the radar rotates under this region, you can just see this huge turbulent feature going from about 400 kilometers to 1,000 kilometers, and highly structured. And what happens when a radio wave propagates through that is it's a lot of interference, and that's sort of a major issue. This is a computer model done by Tatsuya Yokoyama in Japan, one of our colleagues, and he's just modeling this effect. And this is an observation from radar. How does that work? It's basically the same phenomenon, we think, that you get when you, it's called the Kelvin-Helmholtz instability. When you basically have a heavy fluid on top of a light fluid, it should be stable, but if you get any perturbation of that bottom edge, the two fluids start to interchange, and you get these fingers of the light fluid popping up through. And those fingers bifurcate and give you all kinds of structure. So that's what's causing this. On the big picture, you can see this image is from the timed satellite, where they have an ultraviolet imager, just like we saw an ultraviolet image of the sun. We haven't had that many ultraviolet images of the Earth, but the Gold mission and before that timed were giving us these measurements. And basically what they show is these two bands of high electron density around the equator. This is the magnetic equator. And these two bands are called the Appleton anomaly. So if you're familiar with low latitude radio propagation, you'd be used to these, where the density is maybe 2 or 5 times higher than outside them. And then you get, maybe you can't really see, but there are these sort of tiger scratches, like somebody's scratched through these things, you get these dark stripes. And those are regions where the density has gone through these kind of bubbles, plasma bubbles, where the bubbles are rising up through and changing the plasma density there. So these things are typically low latitude phenomena. There are versions that happen at high latitude as well, if you're trying to make those communications. Last one, fill off with a couple of things, like we do also use net radio emissions as diagnostic tools to understand our universe. This one is a ground-based VLF receiver in Antarctica showing a whistler, which you may have seen many times, sort of in the kilohertz range, several kilohertz range. This dispersive signature is the high frequencies arriving first, and then it goes as it comes to you. And you can do multi-hop whistlers and so on. This is a satellite out in the geosynchronous orbit, essentially, and it's showing all kinds of different spectra from 10 hertz to a few hundred kilohertz. And you can see all these different wave modes, chorus, which I'll show you in a second, different harmonics. It's a very rich radio environment. Some are radio waves, and most of them are actually plasma waves that are not free-propagating waves, but they're different wave modes that exist in the plasma. So those are something we use all the time. As Judy mentioned, those radio bursts from the sun, you can use them to get important information that we couldn't get any other way. I don't know if this is going to work, but I have some sonified data from Bill Kurth and the team, Craig Klutzing and the team at Iowa, where they take these spectrograms and they sonify, which you may have done with your own reception. This sonification maybe is not working. Yeah, okay, well, you could go to the University of Iowa website and download these. And just all kinds of interesting structure in here. Again, the kilohertz range, because that's where this particular interest was. These waves are the ones that actually can take those radiation belt particles and energize them to great energies and knock them into the atmosphere and various things. So they're high interest to us in the science field, but they're also just cool because they have just interesting, as we talked about stamp collecting before, these are called chorus, which really sounds like a bunch of birds chirping. It's like the dawn chorus. You can hear those on the ground, you can hear those in space. On other planets have them too. Last thing I want to go to is just a couple of citizen science things, because I think there's a huge natural overlap between, if we'd been sitting 200 years ago, you guys would have been those Royal Fellow Societies, and you would have been the amateur scientists, right? I mean, that's sort of the same kind of spirit that leads to ham radio, I think. And citizen science is now undergoing a renaissance. There's this period where, kind of in the 50s, 60s, 70s, a lot of science was monolithic and large. I think we're now realizing that you can get a lot of great stuff out of educated, interested people who don't necessarily work in a white coat in the lab, but they may be more in tune with the natural world, or more better observers, or just be more of them so that we can have more brain power to find things. So there's a citizen science webpage at NASA, science.nasa.gov/citizen science, and there are many projects there, things like looking at galaxies and sorting them and trying to, because humans can still do that better than a computer program. But the three that I have are more observational in nature. There's HamSci, which is run by Nate Frizzell at the University of Scranton. There's Radio Jove, which our own Xing Feng down the hall from me is running with Jim Tiemann and Leonard Garcia and the guy that I'll get to in a second, I forget his name. And Aurorasaurus developed by Liz McDonald and her team. And they're all in common is that basically they're enlisting large teams of very excited volunteers, and they're making scientific discoveries. So HamSci is the website. They're actually having a meeting in Scranton in March 2020. I don't know if any of you guys ever get up there. It kind of might be a cool way for you to connect with them if you're not already connected. Of course, you don't have to go there to connect. You can just go onto their website and figure out how to exchange data. But if you want to go meet some people, they're in Scranton in March. Radio Jove and Aurorasaurus, you can go to Goddard and meet them, or they can come out here and talk to you. What is it? HamSci uses these multiple networks. There's one called reverse beacon network. There's one called weak signal propagation network. And they basically are just using your data. You guys are logging all the contacts you make, and you're saying, I'm in Georgia, and they're in Frankfurt, and I made the contact at this frequency at this time. And that's extremely useful data that I think people are just now starting to realize that huge database and carefully cultivated database that people have been putting together for years. We now have the computer modeling capability to do something with that data, which maybe a few decades ago we didn't have. Now we can take those data and deduce that, hey, there was a ray path at that frequency that connected those 2 points, and put that into a model that assimilates that into the ionosphere model and try to better specify what the ionosphere is doing. And so here's the example of contacts that were around the time of a solar flare. So this is 3 hours on each side, or 4 hours on each side of a solar flare, or something like that. Here's the flare, the X-rays from the NOAA-GO satellite. And these different panels are at different times. This is right before the flare, this is a little before the flare. This is sort of just after and during the high point of the flare. And what you can see is the number of signal paths has dropped dramatically. And then the recovery phase, they start adding back in. So just by knowing that, even just in this limited geometry between essentially Europe and North America, you get a lot of information.
They did something with the solar eclipse.
Yes,
we all jumped on there. We're doing contacts.
I bet they did. I actually don't know them, but the next one I have is Radio Jove, which did do solar eclipse stuff.
Okay.
And essentially, there they have this standard kit you can buy. Of course, you guys don't need that, but for people who aren't ham, you may want to go get a 20 megahertz receiver, or they also have spectrograph versions. And it's at HF sort of 1 megahertz to 20 megahertz. And they're looking at ambient signals, solar radio bursts. They're looking at local man-made signals, but they're also using it to measure some of these phenomena like the eclipse. Here's the eclipse path, and what happens in the eclipse is this moon is actually blocking this ultraviolet radiation from part of the Earth. Well, that means that the ionosphere that was right in that umbra, normally they're always bouncing into each other, the ions and electrons. Well, so you're always losing them, but you're also generating them. When you turn off the light, essentially, they start to lose faster than they're gaining, and you get a depression in the density right overhead. And this thing passes through in a few minutes. But you can still see effects like the galactic radio background. Xing was explaining to me that the cosmic background peaks up when the density goes down, because now more of it can penetrate to the ground. I don't fully understand the science here, but basically that's the idea. Is they're enlisting citizen scientists to make observations during that deep. Somewhere you couldn't run out and set up like a bunch of radio observatories, high, just for that one eclipse, but you can make use of all the existing facilities that are already in use for other purposes. Chuck Higgins is the guy that I forgot, Middle Tennessee State University. And Aurorasaurus is Dr. Elizabeth McDonald. She's with us at Goddard, and she's funded by NSF originally to do tweet mining and citizen science aurora sighting reports to generate real-time maps of where aurora are visible. And what I want to point this out, this is not a radio thing, although the aurora and radio propagation often are associated with each other. But the cool thing about this is they're actually doing a cutting-edge science with the Alberta Aurora Chasing, basically this group, but in Alberta, and camera people instead of radio people. And they discovered a new phenomenon, which is not an aurora. It's called Steve, but it looks aurora-like. So these guys were taking pictures of it for years. But they had sort of said, well, maybe it's something else. But by getting together in a group and also in this wider perspective, they were able to say, hey, we've eliminated, that can't be this weird thing, or this weird thing. It's something new. And they've been writing all kinds of papers about it to try to basically identify it, show different pictures from different angles. They actually had citizen science taking from different angles to triangulate what altitude it was at. And it's actually just a really great story. So this is one of those citizen science reports that, like the eclipse or like the transcontinental propagation, you can get real, it's not just a science project, it's real cutting edge science that we did not know about until this team came in and did. So I think that's really exciting. The one last thing, just because Judy had mentioned it earlier, I think it's kind of interesting. This is yet another example of sort of citizen science. These high altitude discharges, again, here's the thunderstorm, we're used to the lightning going down or within the cloud. But there are rare, but not so rare, events where discharges go up. And that serves multiple interests. One is it can create ionization in the D region of the ionosphere, and that can affect your radio propagation, at least momentarily. It can also generate radiation for pilots, as we discussed before. But mostly it's just interesting from a science standpoint. How does the atmosphere work? How do discharges work? We're learning a lot by studying these processes. You can't recreate this in a lab because the density is so low and the boundary conditions are so big. You couldn't make a chamber that can really do this. So the only way to study that phenomenon is in space. And so this is another thing that essentially was a citizen science discovery. The airline pilots have been reporting for years. People said, "Oh, you're drunk or you're too tired," whatever. But of course, they trusted themselves. They're absurd. And one of our professors in Minnesota, Jack Winkler, he was developing a camera to study auroras. Really fast, low light camera in the 1980s. And he went outside in the summer to test it. He was going to go to a poker in January, Poker Flat, Alaska in January. So in the summer, he was testing it, building with one of his students. And they went outside and trained it on the horizon, and there happened to be a thunderstorm there. And they saw what we call the first documented sprite. It's the first scientific paper written about a sprite, but I think people have been seeing it for years before. So again, the citizen science, I can't tell you how important it is and how excited I am about it, because it really opens us back all up to that what we should all do.